So the goal here is to completely look at every effect that acceleration has on a moving body. So far we've looked at two components of acceleration. The normal or centripetal towards the center acceleration, so things just don't fly off, and the tangential acceleration. That tangential acceleration is really the one that matters the most because you're usually striking something with a tangential blow. So, but if we have something like this here, and we have, say, a slot in this, okay? And in this slot here, we have, say, a little disc or a puck, and that puck can actually slide in that slot. So if we look at this here, this angle up to the center of that, we're going to call that theta. We're going to call the distance that it's from the center, that distance right there, we'll call P. Okay? And if the puck is sliding out this way, away from the center, we'll call that positive P dot, which is called the slip velocity. And if it has some omega component to it, so your omega here is your, of course, the angular velocity, which we've already examined. So what I'm going to do is show you how we get velocity, and then from velocity we'll get acceleration. So this kind of flow chart here kind of summarizes everything that we've done this semester so far, because we started off with position analysis. And in that position analysis we said that the vector RP was equal to P times e to the j theta. All right? And then what we did is we took the derivative of this, and when we took the derivative of this, we had a couple of components here. We had velocity first of all, velocity. And we looked at this. If this thing is allowed to slide, there's actually a slip velocity. Most of the time it's fixed, but now it's allowed to slide, so it's P dot times e to the j theta. And you can see why that is, because this red vector here is at angle theta, and it's going, the positive value is moving away from the center. So this right here is called the slip velocity. And then we have what we had before, which is take the derivative of this, you get P d theta dt, which we know can be written as omega. And because we are taking this thing and dropping this down, that the tangential component is off in the direction of the omega, is j e to the j theta. And that is our tangential velocity. And if I take the slip velocity and differentiate that, then I'm going to get acceleration. So the acceleration looks something like this here. You have P double dot, because that thing can be slowing down or speeding up. Slowing down is going in the opposite direction of P dot. Speeding up, it's going in the same direction as P dot. We'll talk about that more in a second. And then we have this right here, which is P dot d theta dt, which again we recognize as omega, j e to the j theta. Right? Then if we take the tangential component here and differentiate that, I get the first one is p dot omega j e to the j theta. And the next one is p, the derivative of omega with respect to time, which we recognize as alpha, j e to the j theta. And then the third one, if we take this, is p omega d theta dt, which we recognize as omega, j squared e to the j theta. All right? Let's go ahead and combine these things. So let's drop this one down here. And this is simply p double dot, I'm sorry, e to the j theta. And that is your slip acceleration. Plus, can't see that? Plus, notice that these two things here are the same thing. So I can drop that down, and that is 2 p dot omega j e to the j theta. This is what we call the Coriolis acceleration, and I'll talk about physically what that means in a second, but that's the Coriolis component there, which is a new component as far as we're concerned in this class. And then plus, if we take this one down, this is p alpha j e to the j theta. This is the tangential acceleration. Because of the j squared here, I'm going to put a minus sign out here. That's minus p omega squared e to the j theta. And so this is the centripetal.
J squared.
What's that?
What j squared?
That was a negative.
Oh, that's the negative.
Right? So that's the centripetal or normal acceleration. So if I further want to write this here, this right here is p double dot plus 2, this is really a vector, so let me put a line under, 2 omega cross p dot plus alpha cross p plus omega cross into omega cross into p. Okay?
That's all that first term?
Yeah, well, this right here, no, I'm sorry. This is, all right. So when you took dynamics, is that EMC 310? So that, you may have seen this equation right here. And so I'm writing this equation to remind you where that's coming from. Okay? All right. So on this right here, I want you to note the direction influence of the Coriolis acceleration is based on the presence and directions of both omega and p dot. So in other words, if there's no rotation, no omega, there's no Coriolis acceleration. If there's no slipping, so if that puck is not slipping either out or towards the center, there's no Coriolis acceleration. Only when there's an omega and a p dot, the slip velocity, is there the presence of Coriolis acceleration. That's what I'm trying to say there. So what I'm going to do now is look at that direction influence. So before we look at the direction influence, let's just look at physically what Coriolis really is from a physical sense. So say if I have a rotating